So we need to consider, of course, getting this theta prime angle graphed and then relate that to technically what theta should be in the third quadrant. So let's go ahead and, as you can see, get our real and imaginary axis set up. We've got a first quadrant angle, 30 degrees. That's theta prime. But we want a third quadrant angle. As we all hopefully remember, a first quadrant and a third quadrant angle have the same tangent. So for our purposes, I'm going to draw my third quadrant angle like so. All right, we're going to calculate theta. Theta is pretty simple to calculate here. With this being 30 degrees, we know vertical angles are congruent, so this is also 30. Really, this is also a reference angle. So as it turns out, we've got what, 180 plus 30, so 210 degrees. So theta is a 210 degree angle. Let's make a note of theta as well as theta prime. And I'm going to write it in radians as well, because we do need to go back and forth on various problems that you'll see on the homework. Go back and forth between radian and degrees. So let's start the ball rolling once again with our de Moivre's theorem with now z to the n. I know n is 5, so z to the 5th, and that's equal to, again, this part of the formula or theorem that I'm going to use. And we've got r, so 4 to the 5th times the quantity cosine 5 times, and I'll use 7 pi over 6 here. Could you use 210? Absolutely. But let's go ahead and use 7 pi over 6. And maybe what I'll do is I'll use 210 degrees in my calculations, but maybe write my final answer in the next step, showing that it could be done with both. But in this next step here, radians is fine, plus I sine 5 times 7 pi over 6. Okay. All right, so if you guys consider the fact that, and like I said, I'll use degrees here, that 210 degrees, but really multiplied by 5, and 7 pi over 6 multiplied by 5. So 18.33 and 1050 degrees. These are the same, it's the same angle, but just this is in degrees and this is in radians. So again, you can do this clearly in both modes. It's just a matter of what the directions call for. In this instance, the answer is going to be the same once you actually take the cosine and sine of this respective value, whether it's degrees or radians. Let me use degrees. As we know, we can convert radians to degrees by multiplying by 180 over pi. Okay, so we're back to what we suspected, 1050 degrees. Okay, that was a good little review for us. So we've got 4 to the 5th power. Let's do that as well. I'm going back and forth here just to kind of start the theorem appropriately. So 1024 times the quantity. Okay, so we've got the cosine of 1050. Now we could take that on our calculators, and in degree mode, which I am, we can do that. And this number may look familiar to us, 0.866. But if it's not completely familiar, well, let's just start thinking about how 1050 relates to a full revolution. There's 1 revolution, 2 revolutions. Okay, so we're left with 330 degrees as a result of subtracting 360 once, twice, and there you go with 330 as the end result. In other words, 1050 degrees lands at 330 degrees. So there's 210, wraps around until you get to this spot, 330. The cosine of which, as we can see, is a 330-degree angle, again from the unit circle. Whether we're using the calculator or not, this value we're very familiar with, thanks to our unit circle analysis back in Chapter 4, is what we're dealing with. So radical 3 over 2. So the cosine of 35 pi over 6, in other words 1050 degrees, is root 3 over 2. And I will do the math once again on the calculator, even though we should all be very familiar and comfortable with the sine of 330 as well. Okay, so that's negative 1/2. But again, on the unit circle, radical 3 over 2 common negative 1/2 is what that particular x and y coordinate happens to be. There's really one final step here, and that's distributing the 1024 to this quantity. 1024 divided by 2, 512, and then just multiply just there by root 3, and then 1024 divided by 2, 512. Don't forget your I. Ladies and gentlemen, that is your final answer, A plus BI form. Moving on, roots of complex numbers. Recall that a consequence of the fundamental theorem of algebra, way back in Algebra 2 when we first learned this, in pre-calc where we had a chance to reinforce it even more, a consequence of the fundamental theorem of algebra is that a polynomial equation of degree n has n solutions in the complex number system. A good example to kind of premise here would be a quadratic. X to the second power has 2 roots, or 2 solutions. X to the third, 3. X to the fourth, 4. So the example that I'm going to address here, and kind of building that explanation even further, let's use a more complicated function. Let's say x to the sixth, and let's set it equal to 1. Okay, just by looking at this, okay, it doesn't look like a nice 6-degree function set equal to 0. We still can identify the number of solutions. There are 6 solutions to this equation. Well, how do we solve this equation? So reflecting on some Algebra 2 and pre-calc skills here. So if I solve this, well, as it turns out, this is a difference of 2 squares. And the difference of 2 squares, in this instance, leads to the product of x cubed plus 1 and x cubed minus 1. In other words, if you FOIL this, x cubed times x cubed, x to the sixth, you have negative x cubed and positive x cubed. Those cancel, and then last, well, 1 times negative 1 is negative 1. So very nicely, as you see, it's set equal to 0. We have 2 cubics that we're multiplying. And from here, hopefully we can all, again, bring back from pre-calc that this is the sum of cubes. The sum of cubes has a very specific pattern that we can incorporate. X plus 1 times the quantity x squared minus x plus 1. That's the sum of these 2 cubes. And again, this is a perfect cube, x cubed, and this is a perfect cube, 1. And we'll do the same thing with x cubed minus 1. So the formula plays out in this way. X minus 1 times the quantity x squared plus x plus 1. Still all equal to 0. So we're going to identify 6 roots, one of which is x equals negative 1, one of which is x equals positive 1, probably the 2 simplest ones. And the 2 that remain here and here are going to be a little bit more complicated, which I'm just going to take a moment doing the work ahead of time for you. 1 plus or minus root 3i all over 2 using the quadratic formula. And then again the quadratic formula giving us x equals negative 1 plus or minus root 3i all over 2. Okay, so if you can see here, we've got negative 1 and 1. Those are 2 real zeros. And then lastly, we have 2 imaginaries, 2 imaginaries for a total of 4 imaginaries. Well, gee, guys, what do we got here? We've got 2 and 4. We've got 6 total roots, 2 of which are real. In other words, we would actually see this 6-degree function cross the x-axis at -1 and 1. And then we have 4 imaginaries. 2 here, 2 here. Well, why are we bringing this back? Well, each of these numbers is a 6th root of 1. In general, the nth root of a complex number is as follows. For example, if I asked you again to look at the same problem, x to the 6th equals 1, we can solve this, you would think, just as easily by taking the 6th root of both sides, and you would be right if all I asked you were for the real solutions. So x would be equal to plus or minus, don't forget because it's an even root, plus or minus 1. But what about the imaginaries? Okay. Well, let's continue and see what we can do with this with relation to the definition of an nth root of a complex number, as we see here. So the definition of the nth root of a complex number. The complex number u equals a plus bi is an nth root of the complex number z if z is equal to u to the n, which is also then equal to a plus bi. Look familiar, I hope. That complex number raised to the n power. In turn, nth roots of a complex number. For a positive integer n, the complex number z equals r times the quantity cosine theta plus I sine theta has exactly n distinct nth roots given by this particular formula. And I want us to highlight this, as it does have huge significance here in what we're about to take a look at. And before I get into the example, I want us to draw yet again another real and imaginary axis. This time I'll label it real and imaginary. I'm going to draw a circle. Okay. This circle, maybe we'll draw a point here in the first quadrant, another point that's maybe 2 times that angle. I'm going to call this 2 pi over n. So it's a fraction of 2 pi. The fraction would be n. So it could be 2 pi over 6, for example, or 2 pi over 12, that kind of thing. Multiplying it by 2 times the quantity 2 pi over n, and so on and so forth. So an angle here, here multiplying by 2, you can multiply by 3, and so on. I'm going to point out, to make a connection to this formula up above, I'm going to draw and make a connection to the nth root of r as simply this angle. And according to how you would interpret this particular angle value, yes, from this point all the way to here would be in fact 180 degrees. But for our purposes relating the r and n value, it is technically the nth root of r. Knowing n and knowing r, we can find that quantity. And it doesn't just apply to the unit circle. But again, as far as this particular formula, just to highlight, we have the nth root of r times the cosine of theta plus 2 pi k all over n plus I sine theta plus 2 pi k all over n, where k is equal to 0, 1, 2, all the way to n minus 1. We're going to use really every part of this formula as we go ahead and take a look at the next example. For homework, I do ask that you read the proof of this formula on page 472 through 473 in your textbook, just to kind of get an idea of what this particular formula entails and where it comes from. The derivation is very interesting. It might help in your understanding, even more so. Okay, so example 6. Find the 4 fourth roots of 16. So there are really three major components that I want to highlight.